get started. Very good morning to all of you. My name is Sandeep. You might have seen me briefly during the orientation for this cohort. So I'm a faculty at the EC department at IAC Bangalore. So my expertise is around Graph ML, Graph AI, Graph neural networks. I also have a background in signal processing and more generally data analytics. So I'll be handling module 4, which is one of the important modules for any data scientists to have in their toolkit. It will be on deep learning and or neural networks. Okay, so you will be seeing me for about 6 weeks during this program. I'll be taking you through different aspects of deep learning. We'll see what all we will cover in this in a second. Uh, so you can reach out to me on this email ID during the program or even afterwards if in case you require you need to talk to me. So this is my email ID. And the office hours is particularly 5:30 to 6:30 on Thursdays. So please reach out to the folks at Talent Sprint who will coordinate the meeting schedules. Typically, these slots are for 10 minutes. In case you feel that there needs to be some longer discussion, it could be something of clarification nature for something that's not clear, or you would like to repeat a particular aspect from the lectures, or it could be a more generic discussion that you would like to have, or a brainstorming related to one of the capstone projects or assignments. Please try to make use of these office hours. Thursdays, 5:30 to 6:30, that will be through Talent Sprint, right? So they will handle the scheduling. And of course, you can also reach out to me via CDS support or directly write to me. Often, if it is something related to the program, better to route it through CDS support. So in case I happen to miss these emails, there is somebody overseeing that so that they can remind me. Okay, so I doesn't matter the module number, but it will be on deep learning, right? So that's what it will be on. Okay. Uh, modus operandi, before we get started, all of you are used to the online instructions during the past few weeks. But needless to say, let us try to respect that we are a large class, about 113. So please keep yourself on mute. There'll be enough chances for us to interact during the class after the lectures. I'll tell how I'll operate in particular in a second. But during the lectures, just to make sure that whatever I have prepared to deliver, uh, I managed to cover that. Let's not try to interrupt the flow. In I'll whenever there is any question, please you raise your hand. I'll monitoring the chat window. So most of the questions will be in the chats. You put a question in the chat. If it is really relevant for that particular concept that I'm discussing, I will answer that question. Otherwise, typically what I do is, as we know, we have two 1.5 hour slots, 90-minute slots with a 30-minute break. So typically we start 9 to 9:05 is what I would start. Please be there at 9. If you are there at 9, we can start at 9. 9 to 10:30 is the first slot. And then what I'll do is 10 to 10:30 is the break. I will join somewhere around 10:50. Okay. So 10:50 to 11, I'll also take a short break, come back at 10:50, 10:50 to 11. All those questions that were not relevant for that particular concept, but okay, there is a question in any case. I will handle those questions. Again, we will be having a lecture from 11 to 12:30. Again, I'll hang around a bit for 15, 20 minutes in case there are any questions that need to be addressed. But most of the questions should be on the chat. Okay, so that's the modus operandi for how we will be handling the cohort. Okay, so uh, I hope so far you have been enjoying the previous modules. I hope you do so and continue to do so in this module as well. We'll start with a formal treatment today, particularly going back in history. Deep learning as such, many of you might be aware, is not a new tool as such, right? It has been around for quite a few decades, but due to advancements in compute and renewed interest, it has seen its ups and downs, and particularly we are riding the hype at this point, the peak of its hype, I would say. In particularly, given that the two Nobel Prizes in different fields are somehow tied to AI and deep learning. So that is the times that we are currently in. And especially because of the compute, the cheaper compute, and mostly free compute, right? So many of you would be using or have already used Google Colab, which is almost free, although they kick you out very frequently and not let you use for long durations or large compute. But nonetheless, that is more or less free, right? In case you would like to try out some pedagogical examples, anybody could basically do that just with a Gmail ID. So that is how accessible this technology has become compared to what it was when it was initially conceived. So the roadmap for today is the following. What I'll do is I will introduce this particular module, uh, go back in history, and formally introduce what we mean by deep learning and what is at the heart of deep learning, which is the multi-layer perceptron. This is the basic foundational model for any deep learning architecture that you might have seen or heard about, be it for imaging, speech, language models, etc. Multi-layer perceptron, the basic notion is what we will see today. And the tasks you will see, right, that we will discuss in this module uh, need not be something new. Deep learning means doesn't necessarily mean you're solving a new problem as such. Any problem that you will often encounter can be formulated or casted as one of the two basic problems that you might have already seen in the previous module, that is classification and regression. But what you will be seeing in this deep learning module is you make an abstraction of the problem, not rely on what task you are solving. You have a generic black box that you can use for classification, regression, and the way you train it is also quite generic. It's a generic purpose tool that we will see, and that can be still used to solve the good old problems. Oftentimes, it will be an overkill. You might not need if you're simply doing a classification task on some of the toy data sets. Deep learning, okay, it will give you some insights and maybe an improvement in the accuracy, the second decimal place or the first decimal place need not be super efficient. It might be an overkill, but for larger problems, larger tasks, it is giving you a generic purpose tool that, or a hammer that you can basically use it to for any nail that you would see. The last part, typically what I have been doing in the past cohorts, which people have been liking, and I'll continue to do so in for this cohort as well, is that there is a material towards the end on something called as tricks of trade. which basically involves the nitty-gritties of getting a neural network to train and get it to work. It involves various aspects about hyperparameter tuning, etc. So what I'll do is I'll not cover that during today's lecture. I'll leave it as a self-reading. The way you should process this is as follows. After today's lecture, you will have an assignment session, right? Before the assignment session, just quickly glance through the material under the tricks of trade. And once you do that, go through the assignment, play around a bit, then revisit this material. Okay, then you will be able to appreciate this more. And what I'll do is next Saturday, when you again see me during week 2, I will touch upon some of the important aspects, not all, but a couple of things that's worth mentioning. Okay. So that is basically the plan for today. And of course, deep learning, we can go on. It's usually a semester-long course in any regular program. We will not be able to cover every aspect of deep learning, go a bit more in, go over everything in detail. But in the 6 weeks that we have, we will make the best out of it to give you a formal introduction with a right balance of applications and math whenever required as deemed appropriate. And this should basically help you to process and understand any new development that you would see in the over say a new conference paper that you would read or any new material that you come across. Given this background, you should be able to process and appreciate that. That is the goal of this particular module. It's not the goal is certainly not to check everything. I'll try to, of course, cover most of the things. Speed is not the criteria to make sure that the material is conveyed and most of you understand. That is the goal of this module. Okay. So, by the way, in case there are any issues related to internet, voice is not okay, etc. So don't wait till the end. Such things are crucial. Let us know. We'll try to resolve. There could be outages in the internet or audio might not be okay. So don't wait till the end. Okay. So maybe there is an issue with the module numbers, but I'll try to let's ignore the number from the comments that I see. But what we should basically contrast this module is the machine learning module that Deepak was handling, where you were solving tasks like classification, regression, and you might have come across various tools, right? So various tools for linear, for example, linear regression, classification. There are many tools like starting from gradient boost to logistic to softmax regression, multi-class classification, many tools. But most of these tools, in order to use those tools, what you require is something known as feature engineering. So for example, I'll use this as a running example in the good part of today's lecture. What you see in the left is a picture of a flower. This is a classic data set. This data set is basically a pedagogical one, which is used to classify flowers into three classes. Okay, so there are flowers, images of flowers into three classes. Now, if you would like to use a machine learning tool, the way you would use that is you cannot directly feed in images. What you would instead do is you would extract features from these data sets. And in particular, for this example, a feature would be what is the width of a petal, what is the length of a petal, what is the length of a sepal. So these are characteristics of what allows you to discriminate different classes of flowers as what is obvious from the picture, right? So if you look at these pictures, these three pictures have different sepal and different petals that is obvious and apparent from the picture. what you would do is you would extract all this. Now, this picture, anybody could basically say you don't need a domain expert to tabulate this information to extract features that, okay, if I have to classify, then okay, if the petal width is this much and the sepal width is this much, okay, that belongs to class A, otherwise it belongs to class B. You don't need to be a botany expert. But not all applications are uh, such domain agnostic or something that is of common sense. So most of these applications that we deal with, for example, if you're doing analysis on medical images, you require a radiologist, right? So some of the things would be common sense, or you would train yourself to identify, okay, this is, for example, a pneumonia or not, looking at the chest X-rays, but everything is not uh, domain agnostic, right? So you require a domain expert who is going to basically tabulate this information, extract relevant features, what is relevant, what is not relevant, the domain expert will tell. And once you have this, you're going to feed this to a black box, for example, a classification or a regression tool that you have seen in the previous module, and you're going to make a hypothesis about what the class is. So you're going to train the model, an ML model in the process, and that is going to give you a particular output. Now, imagine solving the same problem, but I don't know what are the relevant features. I don't want to an extent rely on the domain expert, but I would like to solve the same problem given this image that is all the input. Maybe I have some class labels for certain inputs. I know what are the output labels. I have this information, picture and a class label, right? Class 0, 1, 2. I have that information on the training data. Now, without a domain expert, that means that I don't want to worry about whether petal width, petal length, sepal width, these are some determining factors for the class labels. Without that information, I would like to process that. And deep learning is essentially that tool that allows you to combine the hypothesis for a classification or a regression along with feature engineering. Okay, so that is at a high level what if you would like to contrast between what the traditional machine learning models and the deep learning or the neural models, artificial neural network based models would do is combine these feature engineering along with the task relevant model classification or regression. The output is the same. Okay, so that is basically the contrast between the deep learning or artificial neural networks and the traditional ML models. Now, suppose you have a domain expert with you and he's going to give you some additional information, domain specific feature engineer information. It doesn't necessarily mean that you ignore that. Okay. So it is always better. More information, more fine-tuned information is always better. So you're going to augment that information as well. But what we have is kind of a generic purpose box that takes this input, whatever information you have, and gives you the output, which in this case is the class label, the prediction of the class label. Now, if you wonder, you might have seen this picture, but if you wonder where does ML and DL fit in, actually ML is a broader uh, 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 area, and deep learning is actually a smaller subset of this broader area. AI in general is a technology which subsumes ML, DL, and this natural language processing, which was a part of artificial intelligence. Artificial intelligence is basically a technology that can automate, right? So automate things using some notion of intelligence that it is going to pick up. How is going to pick up? It could be because humans are training those computers to behave in a certain way to solve certain mundane tasks or some complicated tasks beyond what a human could foresee, right? That is what is the notion of artificial intelligence. How you realize that, right? Is one such way to realize that is through machine learning. Deep learning is a smaller subset, right? So machine learning is a broader one. The other important aspect, which is gaining popularity in the past couple of years, is natural language processing, which is also basically an ancient topic, right? So natural language processing, like how humans process language, we would wish that computers also process that. And we have made significant achievements as a community so far in achieving that with the invention of all these uh, 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 transformer models and chat GPT and the likes. Natural language processing itself is not new, right? So the goal was uh, clear beforehand, before the chat GPTs and all the newer architectures. It was the way it was achieved was slightly different. It was rule based, right? So, okay, this is a construct of a language. If I want to process this, this is how I need to dissect the information and put some rules. Now, we are able to learn those rules using a combination of natural language reasoning as well as deep learning models. So that is how we would put ML, DL, and natural language processing. And what is also of interest to this particular module is the intersection, and in particular, this smaller intersection of DL and NLP, which we will cover in this module as we progress. So to set up the context, I have a couple of slides. Why is this module important for data science? I guess it requires little less motivation, but we will do so to see what are the tasks that one could basically try to achieve, right? So, and this spans across different domains. And that is one of the, say, the motivating factors to make these models domain agnostic. Okay, so for example, what we see readily in the slide is that the application span from the day-to-day activities, like you would try to write an email in any of the email consoles that you might be aware of today, like Gmail or even Apple Mail and so on. You try to type something, and the prediction for the next set of words is pretty remarkable, right? So it could be basically taking something from the dictionary it has, but some of the things like, yeah, it is remarkable in terms of the grammar correctness and the likeliness of what would come next, right? So this is kind of easing the task that one would use. And for example, face recognition, image classification, some of the things are also very useful. For example, any gallery or the gallery app in any of the mobiles, it would automatically segregate based on people who would frequently appear in the photos. The places geotagging give you nice compilation of moments, etc. And these do not require any training at your end, right? So there is some model, somebody has trained it over a gazillion images acquired from various places, but you take your mobile, okay, you use it, and automatically you see that, okay, there is a remarkable classification of these faces, and that is very useful, right? It's kind of creating an album for yourself instead of you specifying these pictures should go into a particular album, or it would basically help you to navigate through these image domains, right? So if it is text, you could search, but now if you would like to search, for example, this person, Christine, then there has to be a correspondence between an image and a name. So now the models are also trying to build that for you. And some of the tasks like, yeah, day to day, mundane, how is the weather looking like, or you would like to play something from the playlist or something from the cloud. There are these assistants, AI assistants that realize like Alexa and so on. Now, how is it doing? There is no neural network or any model training that is going on that particular device, but it is constantly listening for this keyword, and maybe it is listening to a lot more than just that keyword to process things. But okay, but in this particular case, it is going to screen through that particular word, and as soon as it sees that word, so there is some kind of a constant listening and a trigger happening whenever you see that word. So that means that there's a lot of things going on, right? So you have to constantly ignore noise, process the speech, clean up noise, look for that particular keyword template, in this case, Alexa or Siri, and then it has to trigger. And once it triggers, it is going to process the command that you would again speak, which means that it has to understand different accents, different potentially languages, and compress that information in an intelligent way to somewhere in the server where it can basically process the task given to it, right? So it's, if you break this down, it's a remarkable feat that is going on and helps you to solve some of the mundane things, right? So when you're driving, you would like to call someone, etc. That's making lives easier. Some of the more complicated things are related to medical imaging. Again, the goal is again certainly not to replace doctors, but to simplify some of the tasks, to pre-screen, for example, especially during the pandemic, where we had these chest X-rays, a ton of these chest X-rays, which needs to be pre-screened, and that can be easily done via a neural network. So you basically pre-screen, get a list of pre-screened images that requires a closer look. Again, AI for healthcare is a very booming domain by itself, which has applications ranging from pharmacology to imaging to maintaining EHR, which is emergency health records, uh, even to diagnosis to the to an extent, right? And I'm sure like many of you might have heard about AlphaFold. If not, after today's lecture, take a moment to go through this blog and also to see why was it awarded a Nobel Prize. It was a 50-year-old problem that was solved using graph neural networks, right? So among other technologies, basically it is going to give you a more 3D structure of a protein, which is otherwise difficult to visualize, right? So you would like to visualize a 3D structure of a building. There are many tools, but for these proteins, which with intricate foldings, the structure is difficult to realize. And why is that required? Once you know the structure of a protein, you could design targeted medicines to cure diseases that are otherwise difficult to cure, right? So DeepMind's AlphaFold is important contribution to the field of medicine and biochemistry, and worthwhile of a Nobel Prize. Otherwise, the other tasks, right? So some of the tasks that ease computation, for example, if you would like to simulate physics based, or designing neural networks, drawing inspiration from physics, physical models and equations of physics is again another very important area that is getting significant attention, and many people are working towards it, making significant contributions. Again, this is an application of graph neural networks where you would see in the animation that there is some simulation going on, which means that, okay, I pour a liquid in this particular container. How does it behave? Now, if you would like to model such simulations, there is heavy math underlying differential equations, etc., that would explain the process. This is an approximate model, of course, right? You would like to model this through complicated equations, and you would try to simulate that. Why is that important? For example, if you want to figure out if your airplanes that we normally fly is going to survive certain turbulence, you need to simulate before you put humans, right? So simulators are very important. Similarly, like if you would like to see if the dams that you build are going to survive the stress and the strain it takes, you require simulators. So simulators are very important. Uh, the cartoon is of course nice, but in reality, those are the applications. But now imagine that I don't know what is the right differential equation that I need to use, or we don't have the domain expertise for whatever reason, right? But now what I know is I know how it behaves in reality. Now imagine a scenario where I show hundreds of images or video frames by pouring liquid in different containers and see how it behaves, right? So basically generate a lot of data. And now the question that one could ask is, can we simulate such scenarios or learn what is the underlying differential equations that would best explain it? So this is computationally challenging task, and neural networks are remarkable to this. So these are some of the applications. You could, of course, try to ask ChatGPT. It is in a nascent stage, but it requires it's not necessarily as simple as I'm telling. It involves, of course, a lot of structural equation models and understanding of physics. ChatGPT is, although it is very good, it is at times very dumb, right? So we should always take that with a pinch of salt. It has its own positives and negatives, uh, but if you look at the development in the past uh, 10 years and zoom in the past 5 years, what we have achieved as a community is pretty remarkable, right? So uh, given that one should definitely be curious to learn what is this deep learning and what can we achieve with this. So I hope yeah, you're as curious as I am with this field, and we would like to see what is going on in this module. So, what do we learn? Now, we have 6 weeks. The way I have distributed the content in the 6 weeks is as follows. There might be a spillover from one week to the other, but this is what we are going to broadly cover. As I told, some of the lectures might require a much slower pace. The goal is again not to check tuck 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 and finish off everything, but to go through some of the things a bit more in detail. Things which where I can speed up, I will certainly try to manage the pace. But this is what we will roughly cover in 6 weeks. So we'll start with multi-layer perceptrons today. We'll see what that is, and then multi-layer perceptrons as such. This is for tabular data. The way you should see this is as follows. We have inputs as tables. Okay, that is tabular data. Now, whenever the input is images, we'll see why can't we use the tool from week one, that is multi-layer perceptrons or MLPs in short. Why can't we use this for images? What happens if we use that for images? Or do we need to specialize this MLP to something which is very popular in the vision, that is convolutional neural networks? There are modern architectures which are a combination of convolutions and the so-called transformers. We will not go into transformers in week two, but we will reserve that for week six. But then I'll try to connect how you can use that for images as well. So week two is for images. Week three, we will be worrying about sequences or time series. We will see that again. Why can't I simply use tools from week two or week one for handling time series. Okay, so what happens if we use that? Week 4, we will digress a bit and look at what is another aspect of deep learning, which is generative AI. Okay, so that is how to generate, for example, images, voice, how to generate more data. That is what we will see in week 4 under generative models, generative AI. We will see what is the basic notion of generative AI. We'll see a couple of architectures of generative AI like autoencoders, VAEs, and GANs. And then week 5, we will look at a very important, again, booming area of research is for relational data spaces. Whenever you have knowledge graphs, whenever you have network data, how should we fine tune again whatever we learn in week 1, multi-layer perceptrons, to handle relational data, right? So graph neural networks is what we will see in week 5. So the way you should see this is as follows. Week 1 is very important. Specialize week 1 in a certain way. We have week 2. Specialize and add something to week 1. We get to week 3. Week 4, it's a new philosophy altogether, but week 4 can be realized. To realize week 4, we require week 1, week 2, and week 3. Okay, so you can have a generative model for generating time series, or you can have a generative model for generating images, right? Or you can have a generative model for generating tabular data. So that is the connection between the weeks that you should see. Week 5, again, you can think of a generative model for week 5, or you can have a generative model in combination with time. I mean, graph relational databases could be varying with time. It could be relational databases of images and so on. So we'll be specializing again week 1 to go to week 5 in a certain way. Week 6 is on natural language processing. In particular, we'll be looking at deep learning or neural network, artificial neural network based natural language processing. Again, natural language processing itself, if we start discussing, we can go for 6 weeks. For NLP itself, it involves a lot of pre-processing information, which we will ignore. I will highlight maybe in 15-20 minutes or so, but what is important is to see how we can use these deep learning models for natural language processing tasks. In particular, I will look at one very important architecture, which is basically what is there in all the variants of ChatGPT type models that you would see, with a lot of engineering going on, but we will see what is the base, the backbone of those models. In particular, we'll look at transformer architectures, we'll look at attention mechanisms and so on in week 6. Okay, so that is the plan for this model. So we will see what is artificial neural networks. Neural network is a more apt uh, uh, title for this module. Neural network is a network. We will see what that is, which is something biological, right? So all animals have some kind. All animals with brain have a neural network. The whole purpose of the uh, the drive behind this area is to see if we can mimic what is a human brain doing, or what is a brain of a dolphin or a rat doing, right? So that is, and can we try to reproduce that? And that is why the name artificial is coming there. Now, MLP is a particular way of realizing that goal. And we'll see what is a multi-layer perceptron as we progress. And deep also has certain meaning as we will see later today. But you could use MLP, ANN interchangeably, right? So it doesn't really matter. Okay, now what I would be using to deliver the module is the following material, which is available for free online. There is a newer edition of Geron. You have already maybe encountered Geron in the previous module from machine learning that Deepak was handling. I would be using chapters from that. And if you want to have a first encounter to deep learning without worrying too much about math, but just to appreciate and understand what is going on, for many of you, that might be the goal, right? So in that case, Geron is a wonderful book. Even more so because it comes with this accompanying collection of Google Colab notebooks that you could readily play, right? So without putting any effort. And for that matter, if you're using any libraries like TensorFlow or PyTorch, TensorFlow in particular, I'll be covering with TensorFlow and Keras, but one could use PyTorch or many other variants are available out there, depending on which company you prefer. So TensorFlow, Keras, if you go to their webpage, there are also tens of tutorials, which you could basically use it readily without coding, right? So if you want to just try it out for the first time, that is what you would do. The next time you would the best way to learn this is to follow something on Kaggle, take a data set and try to code it out yourself, right? Participate in one of these challenges. So that is what you would do. So first encounter is this book by Geron and the accompanying page. A similar flavor is available in this dive into deep learning. That is also nice, which also has a lot of animations and it's very illustrative delivery. Now, if you want a more mathematical insight, then I would recommend this book by Goodfellow and Bengio. This is deep learning. So first read, I would do Geron or this dive into deep learning, right? So it also has accompanying scripts. If you want a slightly mathematical treatment, deep learning, even more mathematical treatment. I have not put this here, which I got recently, is a book by Bishop. I think the title is Christopher Bishop. Very nice, again, slightly mathematical. I think it is called as deep learning again. Or I mean, if you look for deep learning, Amazon Bishop, it's very difficult to miss that. So I got a copy myself a couple of weeks back. It's also very nice, slightly mathematical, right? So if you're interested in math, illustration plus mathematics, understanding that, if that is the goal, then Bishop or Goodfellow is a nice treatment for that. And needless to say, because of the popularity of this field, both in industry and academia, every day, maybe hundreds of papers keep coming up. It's very difficult to follow and figure out what is a good one, what is noise. It's impossible to do that, right? So even for somebody for whom this is bread and butter, that is a very difficult task. But the other things are popular papers. For example, like, yeah, if you're interested in transformers, there is this paper called Attention is All You Need, right? So by the title, and nobody knew that it's going to become that popular when it was first conceived. But one good way, maybe not to catch up with what is going on, but to uh, basically go back in history, is to see some of these papers that appear in these top ML conferences like NEUR, IPS, ICLR, ICML, right? So, and then see from Google Scholar, the ones that have like a lot of citations, right? That is one measure, maybe not the best measure, but that should also give you the insight into some of the recent trends, right? So say 2023, okay, the paper is getting like 700 citations, then that must be at least interesting to 700 people, right? So that's how I would see that. So that is basically the background logistic information for this particular module. So in case there are any questions at this particular point, we can I can take one short question if there are. Otherwise, uh, I would continue. Yeah, even for doing simulations, you require real data, or you require the way you should see this as follows, right? So some of the cases it is easy to get real data. Some of the cases it is not, right? Some of the cases it is easy to simulate a scenario. Simulate scenario not in a computer, but for example, you have a wind tunnel. Okay, you can basically simulate a scenario realistically in the physical world, right? Not in the digital world. And from that, it's easy to gather data, right? So now, in such cases, the goal is the following. You have shown, say, scenario 1 to 100. Now, you would like to figure out what happens in an unseen scenario, right? So the potential scenario that you might not be able to simulate, or you are not able to perceive that, how is it going to be here, right? So it's a prediction of this scenario itself, right? So that is how we should yeah. So how to follow, there is no one SOP for that, right? So for example, what you should basically do is like while I speak, you can look at something known as Google Scholar. Google Scholar, you can look at uh, using the same example, attention is all you need, right? So now if you search for the paper in Google Scholar, there'll be a citation index, right? And citation index would basically tell how many people are referring to that, right? So that is one way. And then, okay, so you would see a collection of papers, say, for example, from a certain conference proceedings, say from 2 years back, right? And then, okay, if there are like more than 300 citations that uh, uh, that particular paper has got over in the past 2 years, that means that there is something important about it, right? So that is basically like looking. I mean, it is just like following the crowd, right? So okay, everybody is looking at that. That means that either it is noise or there should be something interesting to that. And to figure out its noise that or something interesting to that, that is usually by experience. Uh, but there's no standard uh, operating procedure for that, right? So if somebody is going to pick up that, then yeah, they're going to be superstars in the area. But anyway, uh, yeah. Okay, so with that, let's get started. So what I'll do, as I mentioned, is I will quickly take you through the history and set up the basic notion of how we can realize a computer to solve a particular task. Right? So that is the goal till 10:30, and then we will understand the multi-layer perceptron a bit more in detail as we progress. So as I already briefly mentioned, I'll give you a second to go through this very nice quote. The basic goal of the endeavor behind many scientists starting from 1943 is basically get a computer to mimic a human brain. To, of course, the wish list is that we can recreate a human brain. That to an extent has, to a large extent, has not been successful. But in the process, what we have achieved is we are able to solve some of the nice problems that is of societal impact, and that is also curiosity driven by the process of in the process of achieving this large goal of mimicking a human brain. And also, what we have realized, when I say we, scientists and many people, engineers working in this area, have realized is that human brain or nature is a good source of inspiration. But what we have to accept is the reality that we have to realize that in the hardware that is available at that point in time. So what this basically code is telling that is that we drew inspiration to fly by looking at birds, but then what we have done is something more better. We are able to fly very super long distances, all the way from say India to the farthest place, like I don't know, over the pole to somewhere in the US, like thousands of miles, uh, or go at say Mach 10 speeds with these jet aeroplanes. And we draw inspiration to fly, but not necessarily mimic exactly what birds do, right? So we don't, the best planes do not flap their wings, but we draw inspiration. And we will see that several in the first 3 weeks, how we draw inspiration from nature by looking at what is special about images that appear in nature. That is what we use to design convolution neural networks, how memory operates in human brains to process time series data, and what is basically a neural network, how we can mimic that in today's lecture, right? So the point is, we'll draw inspiration from nature, but not necessarily mimic that exactly, but try to do something better to achieve a certain task at hand. Neural networks as such is not a new topic, right? So 1940s, maybe there are instances where it was also conceived even before that, but it has seen many ups and downs, right? So in the past, like 10 years, maybe, okay, we'll see like, okay, again, somebody would like to do a new, solve some problem using neural network, doesn't receive any attention because of the fact that it is not easily accessible, right? That technology, for example, even today, right? So if you would like to train the GPT type models, it is impossible, right? So for an individual or a company that is less computationally rich, less compared to Google's, right? Who can throw tons of compute resources. It is even today not accessible. But if you want to make inference, like, okay, use GPT, a free version of GPT for some of the, as an end user, that is possible, right? But if you want to retrain GPT, for example, somebody was asking like, okay, if I want to do that for a particular protein fold problem, but that is not simply possible, right? That's might not be of immediate interest to Google at this point, except for curiosity reasons. But it is designed for a certain task. It can process tons of information in the internet, a lot of documents, etc., but maybe not very specific to the protein fold problem, right? Or even like, okay, if you would like to ask GPT with some Indian specific language that is not very popular, then it fails miserably, right? So, for example, like, okay, if you go to some coastal language in Karnataka, like Konkani, etc., that there's no information much available on the internet. Maybe it is available, I don't know, but so it will fail miserably, right? So it doesn't mean that ChatGPT is like the best thing for all, but or even for images, there have been many instances where it performs remarkably well for data sets that it has been trained on. For example, mostly the Western population data sets. But for example, if you look at the Indian specific context, maybe there is not much data available for whatever reasons, not much training has happened, and it fails miserably, right? And there is known cases of bias being introduced, etc. So there is a long road ahead. And But compared to 43 and today, we know what has changed, right? So most of the algorithms, to an extent, like the back propagation, etc., that we will see is not new. It is old, very old algorithms, but with small tweaks. So what exactly happens in a biological neural network? I'm not an expert, I'm not a neuroscientist, but I'll just give you a one-line introduction to what happens. That would help us set up the context when we set up the notion of multi-layer perceptron. So neuron uh, is a cell available to most organisms that have brain, and these neurons are connected, right? So there is a network of neurons, network of billions of neurons in the human brain, and the way this network behaves is as follows. Every neuron is going to trigger uh, an output, right? So it's going to basically give a neural spike, and it does so when it receives enough inputs. Where does it receive inputs from? Receives inputs from the other neurons that it is connected to, right? So it is a network. There's a lot of connections going on, and every neuron is going to spike or not spike, behave in a certain way. And the spike is through the so-called neurotransmitters. It's going to release a chemical uh, as a spike when it receives sufficient number of inputs, right? So that is all the neuroscience that we require to understand what goes on. Now, the goal of this McCulloch and Pitt from 43 is to mimic this simple behavior in a computer using a logic circuit, right? So that has been the first desire of from this 1943, even before asking a computer to do whatever tasks it does today, right? So that's a very simple proposition to ask. And the first implementation of this biological neuron, not even a network, right? So one particular subset of a few neurons, they called it as artificial neuron. So what it does is what it does is the following. So you would like to mimic this neural network with a few neurons to implement certain logical propositions using a digital circuit, right? So if people are from a ECE or a CS background, you would know what an AND gate is, OR gate is, an XOR gate is. These are simple logical propositions, which are basic building blocks of digital circuits or computers, right? So whatever is operating with zeros and ones, a simple implementation of a logical proposition is the first step towards that goal. So what this artificial neuron does is the following. Whenever it receives more than a certain number of inputs, for example, 2 ones, then it is going to output a 1. Okay, that is the logic that a biological neuron was following. And that is what these guys wanted to implement in a logic circuit. And that allowed them to compute any logical proposition that one could think of in the form of and, or, not, and XOR gates. For example, if we look at this equal gate, this AND gate means it gives you a 1 when both the inputs are ones, right? So now when the input is 1 and 1, it receives sufficient number of, C receives sufficient number of inputs as 2 ones, the output would be a 1. Okay, so now if it is a 0 or a 1, it's not sufficient because it does not receive 2 inputs, the output would be a 0. If it is receiving 2 zeros, the output is again a 0, right? So you could now implement an AND proposition. Now, similarly, if you would like to implement an OR proposition, if it is a 1 0, it should get 1 1, a 0 0. So it receives 2 ones as inputs. Out of the 4 inputs it has, the output would be a 1. So with this, one could implement any logical proposition to mimic the behavior of a simple neuron, a biological neuron, artificially, right? So now imagine doing this. Maybe you have done this in the ECE labs. I don't know if they still do it these days. There's a simple breadboard and you could implement these logic circuits, right? So now what you're basically doing is implementing what a neuron does. But what is clear here is there is no adaptability going on, right? So there is nothing to change. This is kind of hardwired. It can implement certain logical propositions, but now imagine that, okay, I see an image, like going back to a running example, I show an image. What would change here? Everything is hardwired. Nothing would change, right? So I show an image and I would like to solve a particular task of being it belonging to a particular class or not. So okay, so is the annotation clear? Whatever I'm writing, is it clear to all?
Yes, of
Okay,
course.
yeah. So, okay, maybe there is a lag at your end, but let me know. So we cannot change anything. You can implement any logical proposition you want. Now, our goal is to change the output based on the task at hand and based on the input. And this model does not clearly allow us to do. So to that end, a few years later, 1957, 43 was the first conception. 1957, this was the time of World Wars, right? So one of the wars, where with that goal to change something, to adapt to the input, a slight modification in the neural model was the artificial neuron was proposed, and that is called as a perceptron. So we are starting again to mimic the neural network, and the way it was done is as follows. So suppose we have inputs x1, x2, x3. The perceptron, which is this, I'll tell what this is. What it receives as input is not simply the inputs, but it is some weighted combination of the inputs. Okay, so what this perceptron receives is this weighted combination x1 w1 with some weights x2 w2 till xn wn. More compactly, it is written as x transpose w. So what is x transpose w? It is a dot product which collects all these x1 to xn and then w1 till wn, right? So this is the w vector. This is the x transpose vector, right? So you do an inner product between these two vectors, you get z that is at the input. Okay. Now, what this perceptron does is the following. It takes a nonlinear, it applies a nonlinear function. In particular, it does the following. It applies a step function. What does step function do? Whenever the input z is positive, it is going to trigger an output of a 1. So whenever z is greater than or equal to 0, it is going to give you a 1. Whenever z is negative, it is going to give you a 0. Okay, so it is going to trigger as before an output. Okay, but the input now is a weighted combination x1 w1, x2 w2, xn wn, where you're going to figure out what this w1, w2, w3 are. These are trainable, adaptable for the task at hand. So for example, if you show an image or the features, x1, the petal width, sepal width, and petal length, and for a particular class, there is a certain combination of these inputs that gives you a certain class label, right? So for example, x2 and x3 might be set to 0, and w1 is what all you need to say that a particular flower belongs to class 1. Okay, so that's how you're going to trigger the output. Now, based on the task at hand, our goal is to figure out what these W1, W2, W3 are, and you're going to trigger an output. You're going to still get a binary on-off value, right? So the output is going to be a 0 or a 1 output as before. Now, with this, you are introducing adaptability. Remember the analogy, birds could fly with flapping wings, but the planes won't. So now what we are trying to do is we're trying to bring that adaptability here through these weights, W1, W2, W3, that with which you're going to combine the inputs to trigger a particular output. Okay. So now this step function, which is going to give you a 0 or a 1 based on how big or small the input Z is, can be changed to say a sine function, which is going to give you a +1, like what we see here. When Z is greater than 0, it's going to give you a 0 when Z is 0 and -1 when Z is less than. So that's just one function. So step function is going to give you a 0 or a 1. Sine function is going to give you something between -1 and 1. Okay. So this was called as a perceptron model, is one of the first neural network model where you have some adaptability. And this was from 1957, where you see the image here was for a simple task to basically distinguish the cards which have been punched on left or right, right? So you basically see an image, and by looking at that image, you would like to figure out whether this was for attendance punch cards where the mark was on the left or right. So that's a binary classification problem. Left is 0, right is 1. So you would like to classify that to see if people are coming to work or not. Okay. So just to introduce a bit more about this perceptron model, what we typically get as data, which is our data that is given to us, is a table for today's lecture where you have n examples. And each of these examples can have p features. Okay. So what that means is I have flower 1, and flower 1 has p attributes, and this is x1 transpose. And similarly, you have xn transpose. Each of this column, each of this vector is a length p times 1 vector. Suppose our features are petal length, petal width, then you basically have two features, p is equal to 2. Okay. If you have many features, say p features, you will have p entries. These are attributes, and you have n such examples. Now, what you would do basically is that you would linearly combine. Okay. So you're basically linearly combining x1 transpose w and passing it through this threshold logic unit. Okay. So which is going to give you a 0 or a 1 output, or a -1 or a 1 output, depending you are using a step function or a Heaviside function. Okay. So now this is going to give you a 0 or a 1, which I will call it as, say, y1 hat. Okay. So for us, the input that you give me is this table, which has n examples, n flowers. Each flower has p features. And you also give me the labels. Label of example 1 all the way up to label of example n. So for each of this example, you give me p features and a label. Okay. So now what you're basically doing is the following. You get this TLU, which is basically a function of W. Okay. So if there are two features, then you will get two W's, W1 and W2. Now, what you would like to figure out is the following. So I have linearly combined my features and linearly combine my features with some combining weights W. That is our hypothesis for the class label. Now, you would like to set some discrepancy, a loss function between your hypothesis W and y1 hat and y, which is our true label. This is our hypothesis for the class. This is our true label. Okay. So once we have this, now this loss function is a function of W, right? So now you're going to optimize this loss over all the examples and figure out what is that W. Okay. So again, to repeat, what we have is we have P features, right? So X11 all the way up to X1P. So for the first example, we have P features. W is a combining weight with which I tell how relevant is this particular feature for the task at hand. So I'm going to do W1 X11 plus W2 X12 all the way up to WP X1P. This is going to give me my Z. For example 1, that is Z1. Okay. Now, once we have this, I'm going to see if I'm going to do a TLU of Z1 to give me Y1 hat. What is this TLU? TLU is the threshold logic unit, which is basically telling TLU of Z will be a 1 if Z is greater than or equal to 0, and will be 0 if Z is less than 0. Okay, so it is going to give you a threshold. It's a unit that performs a threshold operation. Whether it is 0 or 1, it is going to give you an output. Okay, so it's a simple linear combination to begin with. Okay, and you're going to figure out what this W is. For now, it's a single neuron, a single perceptron, which is very similar to what you would have seen in a logistic regression, right? So perfect. That's correctly related by Piyush. This is what you would do whenever you want a single output. Okay. Now, except that you're using a hard threshold. The main difference is that in a logistic regression, you will not use a step function like this, but you would use a slightly smoother version of this, which is the logistic function, right? So it could be debatable whether logistic regression came first or TLU came first, but this is the basic notion of a perceptron. Okay, so now what we have is the following. TLU, the output is going to give you a 0, 1 output, right? So it's a binary output. Now, this is useful if you are solving a binary classification problem. Okay. Now, suppose you require multiple outputs. Suppose you would like to solve a multi-class classification, then what you could basically do is a more generic version of what a TLU is to basically stack these single layer of TLUs one next to other. You do a horizontal stack of one TLU next to each other with the following change. I'll introduce the more generic way of what a perceptron is looking like as follows. So now let's simplify. Instead of P features, imagine that you only have two features, X1 and X2. So now what I'm doing is I linearly combine X1 and X2 with weights W1 and W2 to get the first output. I use a different set of weights to get the second output, and similarly a different set of weights to get the third output. So what I'm doing is the following. the way you should imagine is the following. Each arrow here corresponds to a weight. So let's focus on the output number 1. So you have W output to 1. This is W 1, 2. And in addition to this, we have an additional input, which is the bias term. Okay, now let's go back. Maybe I'll add. Yeah. So far, suppose our feature was X1 transpose. What we did previously is multiply that with a feature vector W. Now, in addition, we also introduce a bias TLU to be more generic. We will see why that is required as we progress. So you're linearly combining. It's a linear transformation. You linearly combine and introduce a bias, which is more generally called as an affine transformation. So you have a slope, you have an intercept. Okay. So now imagine that you would like to control the slope. You can do that with W, and you need to see where this slope line is, the straight line is, you would use a bias. So now you have two sets of trainable parameters, weights and bias. That is going to give you the hypothesis that we desire for the class label for that first example. Okay, so now this is going to give you the first output. Okay, so that is going to give you hypothesis for the first example and the first output. So this is, let's call it as example number, and this is the output number. Okay, now let's go back to that picture again and come back. Okay, so now W1 for example 1 and the bias. Okay, now I want the second output. Why do I want it? Because I would require, say, 2 or 3 outputs, not just a 0-1 classification, but I would like to have a multi-class classification, or it could be a multi-label binary classification. So for example, think of an application where you see an email and you would like to classify it as spam or a ham. That is a binary classification that you could do with one output. Now, imagine that I would like to classify the same email as ham or spam. And also I would like to see if it is priority or not priority, urgent or not urgent. In that case, you're solving two independent binary classification problems, one for spam or ham, the other one is urgent or not urgent. So this is basically a multi-label binary classification. The other case where you would require multiple outputs, again, maybe it's a recap of what you have seen in the previous module, is that you're showing an image, for example, a digit, and we would like to say that if the digit is 1 out of 9, right? So you have 0 to 9 digits, and you would like to say if that digit is a 3 or a 1, then basically that particular output would be 1. Out of 9 outputs, you only have one output that is 1, the remaining ones are 0. So this is basically a multi-class or a multi-class classification or a softmax regression in the ML context. So now what we have done from the previous perceptron model is the following. Instead of having a single output, we now have multiple outputs. How do we get multiple outputs? By simply stacking one TLU next to the other. So we have 3 TLUs, you get 3 outputs. But what these 3 outputs are giving us is more weights. In addition to weights, we have a more generic affine transformation, which is weights and biases. Okay, so you have 3 outputs. Each output is either a 0 or a 1. Okay, and there are arrows each arrow would either correspond to a weight with which you combine the inputs that goes as an input to that particular TLU, and a bias that is going to give you an offset. So more generally, what we can write it as is as follows. This is what you would do for the first output. Now you can repeat this for all the outputs as more generally as follows. X times W plus B. Okay. So this is a single layer perceptron. Okay. So we will understand what this is a bit more in detail after we resume from the break. But for now, what you need to think about is the following. A quick recap. We wanted to mimic a neuron. We had artificial neuron that was not at all adaptable. It was hardwired that would allow us to implement any logical proposition. A slight adaptability was obtained by introducing W's, which are learnable parameters. You train them for a task at hand, but with a threshold logic unit, which is going to trigger an output based on how large or small this linear combination of W's and X's are. That is going to give you a one output. If you want an extension to multi-class classification, what we could do is we could simply repeat these TLU units multiple times, depending on how many other outputs you want. Each output gets a different linear combination. More generally, you get a linear combination plus an offset term. W's and B's are something that we learn. How do we learn that? We will see after the break. And also understand more compactly in terms of matrix vector multiplications, how an output would look like, right? So we will see this after a break. Now we will pause for a break for about 30 minutes, resume back at 11, okay? And I'll again see at, I'll join back basically at 10:50, but we'll start the lecture at 11. 10:50 I will join back in case you have questions about logistics and other things, or any questions that I did not answer at this point. I can take up those questions. So now let's pause for a 30-minute break.